This video illustrates the jump instruction for the single cycle computer. So open up the ViciLab application file, SCC single cycle computer JZJNZ. This will take a few moments to open and prompt you for your ViciLogic username and password. So complete this, and this will configure a remote FPGA on the ViciLogic cloud platform. After a few moments, open the icon for the single cycle computer tabs. Open up the SCC assembly program in the GUI test program folder, JNZJZ. This is a program that initializes three registers, R7, R3 and R2 to values 2, 3, 4 respectively, and then has three loops, 1, 2, 3, loop 0, loop 1 and loop 2. The first has a jump of not 0 and an actual value of the relative instruction address that the program should jump to if R7 is not 0. So the value -1 loops back to the previous instruction if R7 is not 0. The next loop uses a label, and labels are recommended because the assembler automatically adds the actual values to the program during assembly. So it jumps back to this particular label. And the last, again, has two jumps and also uses labels. Assemble the program, transfer it to the instruction memory, and this is the instruction layout in sequence, program counter 0 up to the end label. The program starts with some bits being set to initialize registers 7 and 3 and 2, so I'll keep going till I get to jump of not 0 for register 7, and you may have noticed that these pictures change on the right hand side to represent the active signals in the single cycle computer for the particular instruction. This one is the JNZ instruction. R7 is the source register address, so it's taking the value of whatever is in register 7, which is 1, selecting it through the multiplexer here in the operand fetch. The value 1 goes into the function execution unit. The output of the function execution unit is not used to write to register or special function registers. In this case, one signal output of the function execution unit, NZ flag, is used in the program counter control unit where the instruction is jump of not 0. Also, the signal jump of not 0 is asserted by the instruction decoder for this instruction, and the opcode upper 3 bits of the 16-bit instruction 110 represents the instruction JNZ. The source address is bits 5, 4 and 3, and that source address is used to select register 7 value through to here. To pass this value through the function execution unit unchanged, the instruction decoder deasserts ALU function and arithcin. I can look inside the program. I can look inside the function execution unit to see that while there is a logical operation block, arithmetic block, shift rotate block, and set clear bits, the one that is being used here is this entry on the arithmetic, which passes the value A, which is currently 1, through to the output. And for every F unit out signal, there are flags that are generated. Currently, not 0 flag is asserted, and that's used in the program counter control unit. So I want to get back to the start again, so I'll once again load the program, single step a number of instructions to JNZ. Once I single step this now, it should jump -1 to the previous instruction if the register 7 value is not 0, and it's not 0 at the moment. So inside the program counter control unit, the flag and the bit in the instruction decoder are both asserted. They assert signal J flag in the program counter control unit, and these are some of the possible scenarios in the program counter control unit I'll select in a moment. The value 5 typically would increment to 6, but in this case, because J flag is asserted, it selects through this multiplexer path a signed addition of the current program count value, with the yellow bits and the purple bits are part of the instruction. Bits 12 to 6 are appended to bits 2 to 0 down here, and the upper bit, bit 12, is sign extended. That means if it's a 1, there are 2 more bits that are both 1. If the upper bit here is a 0, then these will be 0. And what this does is create a 12-bit, because the program counter is 12 bits, a 12-bit signed value, which is added to the current program counter. So the fact that it's a signed vector, it can be plus or minus. Inside the program counter control unit, there are multiple paths. This is the current program counter. The path which is active, if I go back from the input to the register, this path, this path, this path, and through to here, this is the signed addition of the current program counter value with PC offset. Those bits that I've just shown you, the yellow and pink bits in the previous picture, it's treated as a signed 12-bit value and added to the current program counter. To show you what's happening, this is the program. Currently the instruction 5 is executing. The instruction is DFFF, that's this value here, instruction through. The current program counter is 5, and this is the program counter control unit logic that I've just illustrated. These yellow bits and purple bits, 2 bits here, provide this value. The 7 yellow bits that are there and the 3 purple bits, that's the binary value. It's a signed number. Looking at that number, it's a negative number because the upper bit is a 1. If I take the 2's complement of this number, by inverting all the bits and adding 1, I get the value 1, which illustrates that this is the signed number for -1. So if I take that value and I add it to the current program counter value of 5, 1 and 1 is 0, carry a 1, 1 and 1 is 0, carry a 1, etc. the whole way up, I have a carry bit at the end which is ignored, but the result is the value 4, and that's the next value of the program counter. When the clock active edge occurs, 4 will be registered in the program counter, and the next instruction will be the instruction at this address. So going back, if I now single step the instruction, you'll see that the blue banner went back by 1 and the program counter is now 4. Now I'm using a decrement instruction, which isn't really the topic of this video, so I'll step decrement and then it does a jump of 0 again, and now register 7 is the value 0, so the non-zero flag or not 0 flag is now 0, and therefore it doesn't select the signed addition. It allows the standard or the default increment of the program counter from 5 to 6, and the program continues to this instruction, a single step. So despite the fact that -1 is in the instruction, it's not selected because the number is 0. Single step. Now I'm decrementing R3 and using R3 in a loop. I also have a flow chart of this program. There are a number of initialization steps for registers 7, 3 and 2 at the start. This is the first loop, which decrements R7 and jumps back by 1 instruction if R7 is not 0. When it was decremented to 0, the program continued. And this is the point I'm at now. I'm decrementing R3 and then jumping if R3 is not 0. Now to a label, rather than using -1, it's much more safe to use labels in case I enter new instructions, etc. And this hard-coded offset address, relative offset, can actually end up pointing to the wrong place. So back to here. Now R3 is going to decrement. It's now value 2, jump if not 0, R3, to jump module 1 label, which actually happens to be 1 previous to this instruction. So the -1 value still applies, all these 1s here and those 1s here, as before, and the program counter, which was 7, is now used through this path to give the value 6. This is the value of register 3 coming through, not 0 flag, NZ flag is asserted, and jump if not 0 was asserted by the instruction decoder. Single step again, and it moves back. And I'll keep doing this till register 3 gets to 0. Now it's at 0, so the NZ flag is now 0. Therefore, it goes back to the typical path, which is just increment the program counter by 1. So again, even though the instruction has these bits defined for a -1 or an add of -1 signed number, because NZ flag is a 0, that path isn't selected after the sign addition. So I'll jump again, and now it just progresses to the next instruction, which is the instruction 8. And here I have jump of 0 this time. Jump of 0 asserts the signal JZ in the instruction decoder. This is looking at register 2. Register 2 is selected through the source address field here 2, the value is 4. It's not 0. And here, as before, the program counter will increment. In this case, the instruction is jump of 0 R2, but it's not 0. If it was 0, it would jump to the end flag. And if you look at this program, 1, 2, 3, that's 3 instructions further, positive direction from the current instruction, which is 8. And if you look at these bits, they're all 0, and these bits there, 0, 1, 1. The upper bit is a 0, therefore it's a positive number. And that value is +3, which is used as a sign offset, but it's not being selected because it's not 0. So we simply progress to the next instruction on a step. I just fixed an issue. This was R2, R1, so now it's R2, R2, and I've rerun the program. Now R2 is decremented by 1, and I step again, and I jump if R2 is not 0 by -1. So you can see that these values are as they were before, and I have a signed offset, and that's the path that's picked. So instruction A goes back to instruction 9, and I do that until R2 becomes 0. It's currently 2, 1, and when it's 0, that jump back does not apply. Instead, it's an increment from A to B, and B is the end instruction, which continues unchanged. As long as the clock continues, that instruction is still executed. You can see the number of instruction executions count here, but the end instruction continues to repeat without writes, reads, etc. Looking back at the flowchart for the final piece, this describes jump of 0 if R2 is 0 to the end label. Otherwise, progress and loop around until R2 becomes a 0. Jump back to here until it becomes a 0, and then do the next instruction, which is the end instruction, and repeat the end instruction until a reset occurs, or an interrupt if an interrupt was part of a program. That's the end of the demo.